Hi, everyone. I want to talk to you a little bit about normal distributions today, or in this video, I should say. Um, so normal distributions turn out to be super important. Now, there's nothing particularly amazingly tricky about them. They are just the most important continuous distribution that we learn about. Now, we'll explain why in a little bit, but um, they're not any particularly different than like exponential or uniform. I mean, they're differently shaped, but they're not they don't function particularly differently, right? And it's still just the same idea of a continuous distribution that we were talking about in chapter 5. So let me flip over to the notes and talk about normal distributions. So this video is just going to be about the normal distributions part of the normal distributions in the CLT. We will talk about CLT, which stands for central limit theorem, in the next video. So the reason normal distributions are important is twofold. Number one, they are the most common naturally occurring distribution of basically anything. So for instance, biological data, right? So how tall people are. If you took all the men in the world and you put them in a room and you measured all their heights and you graphed them, the shape that you would get would be a normal distribution. Same thing for the women, right? If you mix men and women, of course, you get different heights, and it's not exactly normal anymore. But that is true for basically any biological data. Pretty much everything is normally distributed from a biological standpoint. Now, it turns out that lots of other things are normally distributed as well. In fact, the way normal distributions were discovered in the first place was by astronomers who were attempting to measure errors. So they were trying to, like, it was in the days when everything was handmade, very small errors in positioning of the telescope would give you quite different views of the sky. And so it was really, really important to astronomers to get errors narrowed down as small as possible. And in doing so, over the period of, I don't know, 100 years or something like that, maybe more like 80 years, they tried to figure out the distribution of measurements. Like if the true measurement is right here, what's the probability that you'll be off, this much or that much, and in which direction? And it turns out you need normal distributions to model that. And so normal distributions are actually generally derived from, well, often derived from, I don't know about generally, but often derived from random errors from a central value. And if you have something that are random errors where you're more likely to be closer to the correct value, and a central mean, the thing you end up with is a normal distribution. And that's why they come up so much in nature. Interestingly, that is not why statisticians think that they're so critically important. I mean, it's one reason, but it's not the main reason. The main reason is the central limit theorem, which again we will talk about in the next video. So you've probably seen or at least heard of normal distributions before, although you may have heard of them referred to as the bell curve, because that is the bell curve that somebody who says that is referring to. Well, I'll show you here. Let me show you a picture of what a normal distribution looks like. I've got one up on Desmos here. Is that my, yeah. Ooh, come on. There we go. This is what a normal distribution looks like. I've mocked this up in Desmos. If you want the formula for it, it's this. You don't have to remember that formula. I often have to look it up because I don't use it. I don't actually use the formula for anything. But anyway, this is what it looks like. This is a particular one called the standard normal distribution. We'll mention a little bit later. But for right now, let me explain how to do normal distribution stuff in your calculator, because that's what we're going to use these for. You know how when we were doing exponential distributions, we needed to know how much area is to the left, how much area is to the right, that sort of thing. How much, we need to be able to calculate how much area is between two values. Well, normal distributions, the same way, except we can't do the math directly. I mean, I guess we could plug it all into a calculator, but like I said, formula is a mess, and you don't want to be typing that into your calculator all the time. And luckily, you don't have to, because there is a normal CDF and normal PDF in your calculator, unlike for exponentials. And it turns out it's really easy to use. So let's learn how to use that. And yeah, that's what I want to do next. So Every normal distribution is defined by its mean and standard deviation. So the notation, and we're going to use this a lot, so you definitely need to know this. The notation for normal distributions is this, n mu sigma, where mu is the mean of the distribution and sigma is the standard deviation, obviously. And we use the letter n to denote that it's a normal distribution. So the way you find areas in a normal distribution is with the calculator function NormalCDF. Let's pop over to the calculator and I'll show you what that looks like. All right, so you find it in the same place as the other CDFs, it's in distributions. And in fact, it is the second entry. This NormalPDF, which it might seem like we would use, we will never use. We literally have no use for it in this course, not once. And like, don't think that we're going to use NormalPDF for anything, because we're not. NormalCDF all the time. So NormalPDF, what it does is it gives you the height of your normal distribution. So in other words, it would give you like the y value. Like you see how I'm getting x and y here. NormalPDF would tell me what the y value is, the 0.2427, which we care about not at all. The only thing we're going to use these for is probability, and probability is area, not height. So area is that's NormalCDF. That's how we find areas. So let's see some examples. Yeah. So one common thing I should say, normal distributions go to the right and left forever. It kind of doesn't look like it because they get very close to the axis, right? Like if you were looking at this, you might say, oh, well, that seems to stop about 4, right? Can I do that? Yes. But if I were to move over here, you would find out that it's not touching the axis. It's just really, really close. Right? So I'm zooming way in here, obviously. And I could go to the right as far as I want, and it will never touch the axis. Same thing to the left. It's never going to touch the axis, no matter how far right or left you go. It's always just slightly above it. Now, that being said, it gets very, very close, right? It gets really, really low towards the axis. And since we're looking for area, we're mostly interested in this bell curve part of it rather than the very flat tails. So yeah, like it does go to the right and left forever, but the areas are very, very tiny, especially more than about 3 standard deviations. Well, you'll see. So this one has a standard deviation of 1. And so if I go to the right of 3 or to the left of -3, I don't have much area left. In fact, it's less than 0.3%. But let's see how that looks in the calculator. So the reason I bring that up about it going right and left forever is that sometimes we will want to answer a question like this one, like A here. So height of American women is approximately normally distributed with mu equals this, 64.5 inches, and sigma equals 2.1 inches. Those are accurate as of like the 2010 census, something like that. I want to find the probability that a randomly selected American woman is taller than 5'7". So if I want to go taller than 5'7", that means since there's no theoretical upper limit to height, I mean, obviously there's a practical one, but what I really want to do is go 5'7" and up, right? So up to infinity, up to positive infinity. There's no point at which we would stop there because, like I said, normal distributions go to the right and left forever. So if I wanted to do this taller than 5'7", the first thing I'm going to do is turn everything into inches because I gave mu and sigma here in inches, and so I need to do everything in inches, right? So 5'7" inches, well, 5 feet is 60 inches, because 12 inches in a foot, and 7 inches is 7 more inches, so that leaves me 67 inches. So I'm going to have mu equals 64.5, sigma equals 2.1, and I want to go from 5'7" and up. So what do I want to do here? Let me visualize this with my Desmos graph, because I think that's going to be really helpful rather than me trying to draw one of these every time. No, you know what? Let me not do that. Actually, I'm going to do this on a whiteboard because I want to demonstrate the most important thing that you can do to make this easy for yourself, which is draw a picture. This is it's really easy to mess yourself up, especially when you're just getting started with NormalCDF, about knowing what numbers to put in. If you draw a picture, it is basically hard to get it wrong. So that's what I want to do. Instead of using my computerized one, I'm going to do what you should be doing on pretty much every problem and doing this. Oop, a little longer. Okay, so this is N. Mean was 64.5. Standard deviation was 2.1. Both of those are in inches. So right here is 64.5. And what I'm going to do is I'm going to put on the value that we're looking for and then shade in the direction that I want to find the area, just like I've been doing before, of course. Now, if we go back to the worksheet, that was 57 inches, 67 inches. And I want to go taller than 67 inches, so I want to shade to the right. So when I go over here, just make, so you don't have to get this super precise, just try and get it on the right side, basically, on the correct side of the mean. All right, so 67 is bigger than 64.5, so it goes over here somewhere, 67. And then I'm looking for everything bigger than that, so this area here. And so what you're going to do in your calculator is you're going to essentially tell your calculator to find this area. And so the way you describe this area is you tell your calculator what are the left and right sides of the area, and then what is the mean and standard deviation of the normal distribution it should look at. And that's it. That's let me go back over here for 1 second so I can point that out in the notes. A, B, mu, sigma, where A is the left edge, B is the right edge, right? So in this case, A is going to be the left end, which, if you remember, the shaded area was 67. B is going to be the right edge, which was infinity. Mu and sigma, mu is 64.5, sigma was 2.1, right? And so this mu and sigma here, the fact that I need those is why I put it up here, why I labeled my distribution with them. So the left edge is 67, the right edge of the red shaded area is infinity, since it goes forever upwards, and the mean and standard deviation are these guys. And so let's go put that into the calculator to find the area here. So I'm going to go to, let's see where this was. So just to remind you where to find this, it's distributions, second vars, NormalCDF. Lower bound was 67 inches. The upper bound was infinity. So you can put in a lot of stuff here. I think in the notes I said that you could do this E99. Totally fine. This E is scientific notation. So this E99 is 10 to the 99th power. That's what this says. Certainly that qualifies as close enough to infinity that you will never be able to tell the difference in your calculator. I often just do something like this. Right, just put in a number that's much larger than the other ones. It'll be fine. Because remember that although the tail does go all the way to the right, past 3 or 4 standard deviations away from the mean, there's very little area left. You'll even if I did this would be the same to 10 decimal places as if I did 10 to the 99th power. So just some number that's big, some number that's significantly larger than your mean is many standard deviations away from the mean, basically. The mean was 64.5 inches and the standard deviation was 2.1. And notice it says paste. So if you don't get this screen here, which if you're on an older version of the user interface, you won't get this screen. What you'll get is something that looks like this, where you'll hit NormalCDF, and then it'll just give you a left parenthesis, and you have to type this stuff in yourself. So just type it in this order. A, B, mu, sigma, right? The same order I put it in the notes. There we go, 11.69%. So what that means, if we go look at the notes again, what that means was, so the height of all American women follows that distribution that I sketched. The average American woman is 5'4.5". Standard deviation is about 2.1 inches. So if you gathered every American woman into one room and just measured all their heights and graphed them, made a histogram out of them, the histogram would look basically like this. right? It would look with a mean of 64.5, it'd be bell-shaped right around, with the peak right around 64.5. And so what you're finding is, okay, what percentage of all of those women lie in this red area? That's what NormalCDF is telling us. And it said that 11.69% of women fall in this are in this area. So that means that we think that about 11.69% of women, is that what it was? 11.69% of women, of American women, are taller than 5'7". That's it. So we do the same thing for shorter than 5'3". So if I do short, so 5'3" is 63 inches, right? So this is 60 inches and 3 more is 63 inches. And I want to know what proportion of all American women are shorter than 5'3". So I can use the same drawing for this since it's the same distribution. This is still the same American women. Or this is still the graph for all American women. So 63 would be, here-ish, 63. And I want to find to the left, right? So, pardon my shading. I'm not a big fan of trackpads, but it's what I've got. So I'm looking for this area here. Notice I drew this a little bit closer. You don't really have to be this precise with it. I drew this a little bit closer because this is 1 inch and a half. This is 1.5 inches here, and this is 2.5 inches. So I tried just to make it look a little bit closer. Because this is the 63 is closer to 64.5 than 67 is. You certainly do not have to do that. This is just a visual aid to help you put it all into your calculator correctly, essentially. That's really what this is for. So here I want to go 63 into the left. Now, when you're putting in the left edge here, there's an interesting, not exactly conundrum, but there's an interesting way of thinking about this. If I'm thinking about this in a purely mathematical standpoint, I should put in negative infinity as my left edge because this distribution goes all the way to the left. It goes to the left forever. However, if I'm thinking of this as the heights of a bunch of American women, I should probably stop at 0, right? Certainly you can't have any women shorter than 0 inches. And in fact, from a practical standpoint, of course, you probably can't have somebody much shorter than about 2.5 feet, right? The smallest person you can think of can probably be no smaller than that, something around that area. I'm going to ignore that practical part of it and just go 0 to 63. I'm going to do both, right? I'll do 0 to 63 and I'll do negative infinity up to 63, just to show you that it doesn't make any difference from an answer standpoint. We're going to get the same number either way. So let's go do that. All right, so I'm going to go to NormalCDF. CDF. And so lower bound is going to be, I'll make it 0. And upper bound is going to be 63 with the same mean and standard deviation. And I get a number. This should be bigger than this number, right? Since just thinking about what the area looked like, this was like 11.7%. This one should be a little bit larger. 23.75%. Sure, a little bit bigger. What if instead of 0, though, I used negative infinity or just negative some big number? Let's see what that looks like. CDF. So what if I do negative, like there, negative 1 million? Is that 1 million? Yeah, it's 1 million. Oh, hey, exactly the same. Look at that. So these two numbers are not actually the same. They're just the same as far as the calculator will display them, which I believe is 10 digits, right? Yeah. So this is 10 decimal places here and 10 decimal places here. And so this number and this number are the same 2 10 decimal places. Somewhere down along the line, they would be different, but it's such a minuscule amount that it really doesn't make any difference, right? We're calculating probability here. I don't care if it's, I don't care about the difference between 23.752518751 and 23.752518752%, right? It's so far, it's such a small difference that it's completely insignificant. So we're going to just basically ignore that. So from a intuitive standpoint, it probably makes more sense to use 0 here, just so that you're keeping in mind that it really is a distribution of heights. Minimum possible height is 0. From a practical standpoint, it makes no difference. It makes no difference at all whether you're thinking of this as negative a million, negative infinity, or 0. They're all very close to each other in terms of probability. So yeah, so there you go. That's all I really want to say about that. Let's switch back to the notes so we can. Oops, hello, computer. There we go. So they've started hiding the controls every time you scroll away from them in Zoom, and it's really annoying. All right, we're going to do at least 6 feet tall, between 5'4" and 5'8". We'll do those in just a second. I wanted to quickly make a point though, where here I said taller than 5'7". Here I said at least 6 feet tall. If you remember from the last video on continuous distributions, turns out there's no difference between those in continuous distributions, right? At least means greater than or equal to. Taller than means just greater than. But in a continuous distribution, there is no difference in the probabilities there, because probability is area, and including one particular line does not change the area, right? Because the line has no thickness and therefore no area. So again, this is one of those things where conceptually these should be different, right? Taller than and at least, greater than or equal to. But from a mathematical standpoint, an area standpoint, there's no difference at all. So at least 6 feet tall, 6 feet is 72 inches. So I'm just going to do 72 up to infinity, right? So let's go draw a picture for that. This guy, so actually, you know what I'm going to do? I'm just going to clear all this. So my usual go-to is draw a new picture for, hello? Is it not? Oh, come on. Draw a new picture for every part, right? Just get in the habit of doing this a lot. It's really helpful to draw pictures, and don't be shy about doing a lot of it. It doesn't take long at all. So there's the mean, and this one was 6 feet, which is 72 inches. That's above the mean. So I'm looking at this area here. So 72 to infinity, with a mean of 64.5 and a standard deviation of 2.1. Let's go with that. So we've got CDF, mean lower bound of 72, upper bound of a lot, mean standard deviation, same, very small. So in addition to the or equal to part of this problem that I wanted to point out, I also wanted to point out this. The E-4. This is scientific notation, and one of the most common mistakes that my students make is reading about 3 numbers in and then literally not even looking over here. That's not a good idea, because this is telling me this is not 1.77 here. This is 1.77 times 10 to the -4th, which means take this decimal place and move it 4 to the left. So it is, well, here, let me annotate that. It is this. So let me do it this way. So we move 1, 2, 3, 4, and these guys are all zeros. Point. Right, so 0. There's a decimal there. That's what that is. It's 0.000177. That's what this is. Right. So this is much, much smaller than 1.77. It is, in fact, 10,000 times smaller than 1.77. So you got to notice this stuff. You cannot skip that. That's really important. You should, by the way, if you see it, like, so what we're finding here is a probability, right? It's an area. It has to be between 0 and 1. We know that from probability. So 1.77 is not a probability. Like, that's not a thing that can be probability. That would mean 177% or 177.5%, right? Which is not a probability. It's got to be between 0 and 1. This is one of the most common mistakes I see students make, which is they will just kind of blindly write this number down without thinking about what it means. What we're finding, here, I'm going to erase all this stuff. What we're finding when we do this is I'm looking for the probability that a randomly selected American woman is at least 6 feet tall. Well, it's not 177%, right? without doing any further work, I can tell, without even knowing what the answer is, if you put 1.77 for this, definitely not. Definitely not. It's supposed to be a probability. It's got to be between 0 and 1 or 0 and 100%. Right? So it is 0.00017, I guess 178. I've been saying 177, but it's 178, which is 0.0178%. Right? Tiny. Very, very tiny. All right. Last one I want to do. Between 5'4" and 5'8", so 5'4" is 64 inches, 5'8" is 68 inches. We're not going to infinity in either direction here. Here, what we are doing is going between two numbers, so 5'4" and 5'8". So there's my whiteboard. So we know that that is, so 64 inches is barely to the left of this, of the mean, and then 68 inches is over here somewhere, right? So I obviously haven't drawn this very, very well to scale, but that's fine. Again, it does not matter if you get it to scale or not. We are just really trying to make a visual aid here. So I'm trying to go between 64 and 68, so that's what I'm going to put in as my left edge and right edge, right? I'm going to do normal CDF of 64, 68, 64.5, 2.1. So let's go do that. Normal CDF. Lower bound was 64, upper bound was 68. Standard deviation. Now I'm expecting this to be a big number because it was including here. I'm gonna do this for 1 second. Oop, that's not the right thing. I meant, oh, come on, scroll down. Okay. What I meant was, so I'm expecting this to be a pretty big number because this includes the peak. Generally, if you're including the peak, unless you're really, really skinny, it's going to be a pretty big probability, right? So I'm expecting this to be a relatively large number. Paste. And yeah, pretty big, 54.63%, right? No scientific notation. This is just 54.63%, so pretty big. All right. So that's normal CDF. Normal CDF finds the area in a normal distribution. In general, that's what you're going to want to do most of the time. When we start doing hypothesis testing, we'll do this a slightly different way, but it's still the same general idea of find the area in a normal distribution, normal CDF. Same way we did binomial CDF. I guess there was an exponential CDF, was there? Poisson CDF, geometric CDF, right? Normal CDF finds the area. Now, calculate, because we end up using inverse, or we end up using normal distributions so often, your calculator has another function called inverse norm, or I guess they just call it INV norm, which is a little annoying, but it's INV stands for inverse. So inverse norm gives you the percentile in a distribution, or that's you tell it what percentile you want, and it tells you what the data value would be for that percentile. So what I mean by that is, well, this. So I want to find the 10th, 75th, and 99th percentiles of American women's heights. So what you do is you put in how much area you want to the left of a certain number, and then your calculator tells you what the certain number would be that has that much area to the left. So let me help you visualize that, because I feel like I'm not saying that all that well, but it's pretty clear when you see it. So this is what I want. So what you would do, for instance, is you would tell your calculator, okay, I want this shaded area right here to be something, 10%, right, to be 0.1. And that would give you the, and then what it will tell you is what this number is, right? So you tell it, okay, I want the area to be 10% here, and your calculator says, okay, then the number that you are looking for with 10% to the left of it is negative 1.58, whatever that number turns out to be. It's not exactly this. Yeah, so you're telling it how much this is, and then it's telling you what the observation is. So you're telling it the percent, or you're telling it the percentage, and it's telling you the percentile that corresponds with that percentage. So let's see that. All right, so like I said, we want 10th percentile. I'm going to start with 10th percentile, 75th, and 99th. They're exactly the same, or they're not the same number, but you do them exactly the same way. And we're still using the same mu is 64.5, sigma is 2.1, and you still have to tell the calculator what those things are because it still needs to know what normal distribution you're looking at. So you put in how much area you want to the left, and then mean and standard deviation, and it tells you what that data value is. So I'm going to put in 0.1 for 10th percentile, and then mu and sigma 64.5 and 2.1. All right, let's see what that looks like. Inverse norm, it's found in the same place, by the way. It's right here, just number 3, right under normal CDF, inverse norm. Area to the left is 10%. So if you put in 10, by the way, it will not accept that. It has to be in decimal form. Our mean was 64.5 inches, and our standard deviation was 2.1 inches. Now, some versions of TI 83 and 84 have this thingy, where you're telling it, okay, I want 0.1 to the left, or I want the middle 0.1. That's what this would be. Or I want 0.1 to the right of this number. I find that when I'm teaching students to do this, that is very confusing at first. If your calculator does this, feel free to use it. I'm just going to leave it on left all the time and put in how much area is to the left all the time. I'm guessing most of you that have physical calculators do not even have this option and only have the left option. So I'm just going to do that all the time. If you get good with this, it's actually quite convenient. You don't even have to be that good with it, just try it a little bit. But it's actually quite convenient to be able to do this, but also totally unnecessary. Like, this works just fine if you just do it to the left all the time. Anyway, 10th percentile means I want 10% of the area to the left. So that means that the value that has 10% of the area to the left of it is 61.8 inches. Let's go draw a picture of that and see what that looks like. Come on. Okay, so I'm going to erase all this. So that means that in my distribution of American women's heights, I should just draw the bell part first, huh? I always get the, oh no, I got it right that time, good. So I know the mean is 64.5. The 10th percentile is whatever this number is that has 10% of the area to the left of it, right? So this blue shaded area is 10%. That's what's meant by the 10th percentile, right? 10th percentile is this guy right here, right? It's whatever number has 10% of the area to the left of it. And we just found out that it was 61.8 inches. 61.8 inches, which goes quite well with our picture, right? Something kind of far-ish to the left, which is exactly what you'd expect. We'll find the 75th and 99th percentiles, which are the same thing. We're just going to do inverse norm of 0.75, inverse norm of 0.99 with the same mean and standard deviation. So just jam through those real quick. So if I want the 75th percentile, I'm going to go inverse norm, 0.75, right? So there's the 75th percentile, leave everything else the same. And something that's a little bit bigger than the mean, right? The mean 64.5, we would expect it to be a little bit higher than that, which it is, 65.9. So about 70 inches, or about, what is that, 5 foot 10? 75th percentile? Yeah, it sounds about right, right? About 75% of women are 5 foot 10 or shorter, and about 25% are 5'10" or taller. Am I getting that wrong? Yeah, that's wrong. This is 5 foot 6. Sorry. I don't know why I can't subtract there. I was, yeah. Anyway, ignore that. 5 foot 6. So about 75% of American women are 5 foot 6 or shorter, and about 25% are 5 foot 6 or taller. And if you're thinking to yourself, that doesn't sound right to me. I know tons of women who are taller than 5 foot 6, and about the same number who are shorter than 5 foot 6. You got to remember, this is the distribution for all American women, including little old grannies, right? You probably know a lot of 18 to 25-year-olds, right? That's as tall as those people will ever be. And when they are 85 years old, they will be significantly shorter than that from bone density loss and all that stuff. And so you know an abnormally tall section of the population just because of your age. And so this 5'6", 75, the 75th percentile being 5'6", actually does make perfect sense because it includes a lot of, 4'9", 85-year-olds. Okay, so let's find the 99th percentile. Same deal. So distributions, number 3, 0.99. And there we go, 69.38 inches. So 5'9.5-ish, 5 feet 9.38 inches. So I'll call that 5'9.5". So again, 99% of women are 5'9.5" or shorter, and 1% are 5'9.5" or taller. So there we go. That's inverse norm. It finds percentiles. This is how you use it. Let's flip back to the notes and see where we're at. So there's a neat little rule you can use. This is not a thing that is super important, which is interesting. It is a thing that is taught in every statistics class I've ever seen. It's called the empirical rule. The empirical rule is just a rule of thumb to estimate how much area is in certain regions of normal distribution. So normal distributions are kind of all shaped the same in a sense, where if you think in terms of standard deviations rather than absolute distances, then they all have the same area within certain numbers of standard deviations. So let me flip over to my Desmos graph here. So I'm gonna turn these guys off and turn this on. So there's the empirical rule. The empirical rule says that 68% of your data is within 1 standard deviation of the mean. So this purple area here accounts for 68% of all the area under this. 95% is within 2 standard deviations, right? So between the green lines here, so from this green line all the way up to this one, that is 95% of the area. It turns out it's actually about 95.33%, so it's a little bit more, but empirical rule is not meant for precise calculations. It's just a quick rule of thumb, back of the napkin kind of calculation. 99.7% of the data is within 3 standard deviations. So only about 0.3% of the data, or of the distribution, is going to be more than 3 standard deviations away. So that's what I meant by like the vast majority is within 3 standard deviations. And if you want to be, you can go out to 4 if you want. It's like 99. I don't even remember what it is for 4, 99.95% of the data or something like that. Yeah, that's all the empirical rule is. It is not a formula for calculating precisely. It is a back of the napkin, like quick and dirty calculation aid. If you want a precise probability, and in this class we will, use calculator. That's the way to do it. Empirical rule. I use the empirical rule when I'm talking sort of colloquially or trying to get a quick estimate without having to type something in, but that's it. So the empirical rule is basically just 3 numbers. They tell you how much is within 1 standard deviation, 2 standard deviations, and 3 standard deviations to me. So I should point this out. So notice I've got my standard deviation set to 1 here. If I make this a little bit wider, right? So now it's 1.3. It changes where these boundaries are in terms of absolute numbers, right? When the standard deviation was 1, the boundaries were at 1, 2, and 3, right? If I change standard deviation to 1.3 or whatever, let's make 1.2, then they would be at 1.2, 2.4, and 3.6, right? Because if my mean is 0 and my standard deviation is 1.2, then being 1 standard deviation away from the mean means being between negative 1.2 and positive 1.2. Being 2 standard deviations away from the mean means between negative 2.4 and positive 2.4. So that's what when I'm talking about being within a certain number of standard deviations of the mean, that's what I mean, right? Both sides where I'm measuring not in numbers or data values, but in standard deviations. And this, here, I don't know if this was clear or not, but if I change the mean, right, everything moves with it, right? So now my mean is 0.93. Let's make it 1. Right, so my mean is 1 here. So now 1 standard deviation away from the mean is 1.2 above 1 or 2.2, right? And 1 standard deviation below the mean is 1 minus 1.2 or negative 0.2, right? So that's what I mean by measuring in standard deviations away from the mean. And if you think back to, remember the ridiculous way I was asking those questions in, I believe it was chapter 4, about like, what's the probability that LeBron makes a number of free throws that differs from 35 by at least 5, right? That was one of my examples. It's because I was setting up for this, where being 5 away from the mean number of free throws is analogous to being 1 standard deviation away from them. So I just wanted you to start thinking about what that looked like. So that's why I was setting that all up. It was my devious plot to make you think in that way. So let's go back to the notes here. That's all the empirical rule is. Z-scores, I don't remember if we've talked about Z-scores. We've actually used them a couple of times. I might have to move this in the notes at some point. But what a Z-score is a way to compare things that are unlike, essentially. So I'll show you what I mean by that. But this is, all a Z-score is the number of standard deviations away from the mean. So here, X is my observation. Mu and sigma are the mean and standard deviation of whatever distribution I'm looking at. And then Z is how many standard deviations away from the mean it is. I'll briefly explain how this formula captures that, but you're probably gonna have to think about it unless you're really conversant with math formulas. So here's the idea. X minus mu is just the raw distance between those two things, right? If I want to know how far apart X of my observation is and the mean, I just subtract them. To scale that so that we are measuring in standard deviations, we divide by the standard deviation. Now you might say to yourself, I don't understand why you're dividing by the standard deviation. Think of it this way. Let's say that I have 2 things that are 6 feet apart, right? So I have one thing that is, so from where I'm standing, there's a thing that's 4 feet away from me and another thing that's 10 feet away from me. If I want to know how far apart those 2 things are, I would subtract, right? 10 minus 4. If I then want to know how many yards apart those are, so now I'm measuring in yards rather than feet, I have to divide by how many feet there are in a yard, right? So 4 and 10 feet is, they're 6 feet apart, but that's 2 yards. So to change my measuring stick to yards from feet, I have to divide by how many feet there are in a yard. Same thing here. X minus mu, that's just how far apart X and mu are. Here's me changing the measuring stick so that it's measuring in sigmas rather than in raw numbers. That's what this is. So that means that Z is the number of sigmas, the number of standard deviations apart that these guys are. So I'll let you think about that, but that really is all we're doing here. The reason I'm hitting this so hard, by the way, this formula, this very simple formula, is that this idea of subtract 2 things to see how far apart they are and then scale by a certain value is probably the most commonly used measuring tool in statistics. Not probably, it definitely is the most commonly used measuring tool in statistics. How far apart 2 things are, scale to measure in something, which is often standard deviations. The reason we care about this, or the reason we care about this particular thing, is Z-scores allow us to compare unlike things. So for instance, let's say you got I guess the SAT is back to a 1600 point scale. It's 2400 for a while. I don't know if you guys even know that, but so let's say you got a 1200 on the SAT and a 27 on the ACT. Which of those is better? They're both measuring the same thing, but they're scaled so differently, right? And so what we want to know is which of those things is better. And z-scores allow us to compare stuff like that. So I'm going to do a different example of whale versus human, just to see, which of these things which is more unusual. But before I do that, let me quickly hit one more thing, which is the standard normal distribution. There's a particular normal distribution that has a name, and as far as I know, it's the only one, and it's the standard normal distribution. It's the normal distribution that has a mean of 0 and a standard deviation of 1. And if you saw my so this guy, that's how I had this set up originally, right? Mean of 0, standard deviation of 1. Now, the reason this has its own name and the reason that it is more important than other normal distributions is that what used to be the case is we would turn every normal distribution into this one by doing some scaling. We would shifting and scaling. We would subtract the mean and divide by the standard deviation, and you'd end up with this distribution. The reason I care about that is so we don't really bother doing that anymore because we have calculators now. What we used to have to do is, before calculators could handle normal distributions very well, which, by the way, was probably more recent than you think, but it's about 1990, something like that, when calculators were powerful enough to start handling normal distributions. It was a couple years before I started college, and then before that, people didn't really have graphing calculators, and they didn't have functions like NormalCDF in them. By the way, when I went to college, one of my first calculators was a TI 81, 80, something like that. It is very similar to the TI 83. 83s and 84s are more powerful, but not as much as you might think for supposedly 30 years of progress. It had NormalCDF in it, and before that, calculators like handheld calculators kind of just didn't. So statistics started in the late 1600s, something like that. So between the late 1600s and the late 1900s, right? So for about 300 years, you're trying to do statistics, or I guess normal distributions didn't come up until about the late 1700s, early 1800s, something like that. 250 years, let's say. So for about 250 years, trying to do stuff with normal distributions was really a pain, unless you wanted to use this messy formula for everything. What you did was you converted everything into the standard normal distribution, and then somebody just wrote down all the areas in a normal distribution in the standard normal distribution. So you didn't have to calculate them; you could just look them up in a table. If you converted, right? If you converted to the standard normal distribution. So from a historical perspective, z-scores were critically important because that was how you looked up everything about your normal distribution. Was you turned it into the standard normal distribution and then used a book to look it up. We're not going to worry about that so much. However, the reason I care about that is, well, there's a couple reasons. One of them is that the letter Z specifically refers to the standard normal distribution. So if you see the letter Z as your variable in statistics, it's referring to the standard normal distribution, and it's referring to z-scores, because that is what z-scores are. Is they're well, here, let me show you what I mean. So here I am with the standard normal distribution. Notice that one standard deviation away from the mean is 1, and 2 standard deviations away from the mean is 2, right? So the x value here is the z-score, and so we would usually just say that this is the z value, right? And that's specifically in this distribution and only this one. So if you're counting a number of standard deviations, that's what the standard normal distribution has. Like 1 is 1 standard deviation above the mean. -1 is 1 standard deviation below the mean. 2 is 2 standard deviations above. -2 is 2 standard deviations below. So the sign tells you which direction, whether you're left or right, and the size of the number tells you how many standard deviations away you are. And yeah, so that's why the standard normal distribution is so important, is because it just tells you what the z-score is. Like, the value that you get is the z-score in the standard normal distribution. I feel like I'm not saying that very well. Hopefully it will be a little clearer with a little bit more experience. Okay, so I'll do a z-score comparison, our z-score example here, and then we're going to stop the video, which has already run way over because I'm rambling like crazy. So here is my z-score example. Massive female North Atlantic blue whales is normally distributed. And this is about the normal distribution they follow. We don't actually, we're not 100% sure about the distribution of blue whale mass, because we just haven't weighed all that many blue whales, right? This is just the best guess I could find on the internet. 112 tons with for a mean and a standard deviation of 15 tons. Mass of adult male humans is approximately normally distributed according to this distribution. About 190 pounds for the average and about 35 pounds standard deviation. So Sophie here, she's an adult female North Atlantic blue whale, and she weighs 132 tons. John, the adult male human, weighs 260 pounds. So John is the largest human Sophie has ever seen, and she knows she's pretty large for a blue whale, so she's curious if she or John is larger relative to their respective species. All right, so Sophie wants to know, is a 132-ton blue whale more or less unusual than a 260-pound male human? So Sophie doesn't have a calculator, she's a whale, so we're going to have to help her out here. All right, so I'm going to draw sketches of these two things. I am not going to attempt to draw them to scale in any way. I'm just going to draw them the same and label them, right? That's the way I draw all my normal distributions. It's just simpler that way. So I'm going to go ahead and get rid of this. So we've got whales were 132 or 112.15. So whales. This is N 112.15. There's 112, and Sophie weighed 132 tons. And then, yeah, and then adult male humans was 190 something that I forgot. So this is N 190. Pardon me, I'm going to flip back. I'm not going to switch my screen though. 35. 35. So we got 190 here. And then John was 260 pounds. So here, 260. So the question is, which of these is more unusual? Another way of saying that is, which of them has less area to the right of it, or similarly more area to the left of it? Another way you can think of those is, which of them is farther away from its mean, from the mean of comparable things. So mean for blue whales is 112, Sophie's 132. That's 20 tons, right? It's 20 tons between 112 and 132 tons. Is that more or less unusual than John, who is 70 pounds, right? 70 pounds above the mean. So let's see here. So Z sub, I'll call it whale. No, she has a name. Let's call her Sophie. Z sub Sophie is, so it's x minus mu over sigma. So x is the observation. In this case, it's 132. It's the thing that we're trying to find how far away from the mean it is. So that's 132 minus the mean, which is 112, divided by 15 tons, which is the standard deviation. So that we are measuring in standard deviations. That's 20 over 15, which is 1.33. 1.3 repeating, right? 1 1/3. So Sophie is 1 1/3 standard deviations above the mean. John, Z sub j, is 260. So we take John's, oh my God, that's awful. Try that again. 260, there we go. 260 minus 190. So observation minus mean divided by standard deviation. That is 70 pounds over 35 pound standard deviation, which is 2. So John is 2 standard deviations above the mean for his species. So that means that John is farther away from the mean of his species than Sophie is from the mean of her species. So John's weight is more unusual than Sophie's weight. So even though this is only 70 pounds and this is, what is that, 20 tons? So 20, is that 40,000 pounds? Is that right? Yes? Yeah, that's 40,000 pounds. Holy moly, blue whales are big. Okay. Yeah, so this is 40,000 pounds and this is 70 pounds. So Sophie is 40,000 pounds heavier than your average blue whale, and John is 70 pounds heavier than your average human or male human. And yet, John is more unusual than Sophie, right? John is farther above the mean for his species because we are comparing him only to his species, which has a mean of, or excuse me, which has a standard deviation of just 35 pounds, as opposed to this, which is 30,000 pounds. So yeah, that's how z-scores work. They allow us to compare unlike things. We can compare the weight of a blue whale to the weight of a human relative to their species and find that even though this is only 70 pounds above the mean for his species, and this is 30,000 pounds above the mean for her species, he's still more unusual. All right. Oh, I guess we just answered these questions. So yeah, how many standard deviations above the mean are they? John was 2, Sophie's 1.3, or 1 1/3, I should say. And so a 260-pound man is more unusual than a 132-ton female North Atlantic blue whale. I do want to point out one last thing, then we'll go ahead and end the video, which is about z-scores. Notice that these are both positive. Positive or negative just indicates which side of the mean you're on. These are both positive because they're both above. If we had, say, a 155-pound human, right, over here, so 155 is here, then what we would do is 155 minus 190, right, so x minus mu, and we would get a negative number. So negative z-scores are entirely possible. In fact, half of the z-scores are negative because they're the ones that are to the left of the mean. And I think that's the last thing I wanted to say about that. So I'm going to go ahead and end the video here, probably long after it should have already ended, but that's okay. And the next one we'll talk about the central limit theorem, and we'll talk more about why we think normal distributions are so important. So, all right, I'm going to go ahead and end it here, and I will see you in the next one.